Alrighty. Oh, let's see. Let me just make sure. Okay, 1, 2. Yep. Okay, good. Just making sure the audio is on. Hello and welcome to lecture. Tonight we have a normal. We have a normal lab tonight. We've been through 2 weeks of oral exams, and it's nice that things are kind of going to be back to normal for a little bit. So, but anyways. Let's go ahead and dive back in. So in our last lecture together, we were talking about balancing chemical equations, and we're going to continue that discussion now. So we're talking about balancing chemical equations. We are in chapter 5. And I left off last lecture with an example, which was the reaction of nitrogen and hydrogen to produce ammonia. And so we're going to pick up with this example now. So again, as always, we start by taking an inventory of the number of atoms on either side of our equation, because we know that matter cannot be created or destroyed, and so we need to make sure it's our job when we're balancing a chemical reaction to make sure that the same number of atoms on the reactant side are the number of atoms on the product side. So on the reactant side, we have 2 nitrogen and 2 hydrogen atoms. On the product side, we have 1 nitrogen and 3 hydrogen atoms. Now, when you're balancing a chemical equation, this is the rare opportunity in life where the path of least resistance is actually the best way to go. So when I look at these 2 atom counts, I see a 1 and a 2 for nitrogen. I see a 2 and a 3 for hydrogen. Now, 2 doesn't go into 3 evenly, all right? 2 doesn't go into 3 evenly. So I'm going to pretend like that's not even real. Pretend it doesn't exist. Because 1 goes into 2 evenly, I'm going to start there because that's easier. I'm going to ignore my problems and just hope it works out. So let's see how this goes. If we multiply ammonia NH3 by 2, that changes my nitrogen count and my hydrogen count. Now that we have 2 molecules in play, I have 1 times 2, or 2 nitrogen atoms, and I have 2 times 3, or 6 hydrogen atoms. Now you'll notice that nitrogen is now balanced. Hydrogen still isn't, but it wasn't to begin with, so it's not worrisome. We've got 2 hydrogen atoms on our reactant side, 6 on our product side. We can balance this reaction if we multiply H2 by 3. Now that we have 3 molecules of hydrogen, we have a total of 6 hydrogen atoms on the reactant side, and that is the balanced chemical equation. All right. So let's do, so that was the example we left off with. Let's do a new example. Sorry, my notes are kind of small. There we go. All right, so next example. Let's do the reaction between N2H4 dinitrogen tetrahydride. This is in the aqueous phase. Reacting with oxygen gas to produce water, H2O, and O2 gas. Okay, sorry. I hear my kids screaming like being silly, but I'm going to just go ask them to quiet down. Hang on 1 sec. Yo, Quinn. Quinn, I didn't lecture, bud. You gotta stop screaming, okay? Thank you. Love you, baby. Nice. Sorry about that. It's a thing when you have a 10-year-old who's lived through a year of quarantine. Sometimes they just scream indoors for no apparent reason. All right, so let's go ahead and hang on. I was clearly distracted. O2 is a reactant in this reaction, not a product. Sorry. The product should be nitrogen, N2. All right, so let's go ahead and balance this chemical equation. First, by taking our inventory, we have nitrogen, hydrogen, and oxygen on both sides of this equation. All the parents out there can feel me on that one. Totally. All right, nitrogen, hydrogen, and oxygen. So on our reactant side, we have 2 nitrogen, 4 hydrogen, and 2 oxygen. On the product side, we have 2 nitrogen, 2 hydrogen, 1 oxygen. All right? Now, hydrogen and oxygen are both out of whack. I'm going to start by looking at oxygen because it's the simplest. I've got 1 on my product side, 2 on my reactant side. To balance oxygen, I need to multiply H2O by 2, right? So I get 2 oxygens on my product side. But it also changes my hydrogen count. And you'll notice, in this case, it actually balances the entire reaction in one fell swoop. You hit that water with a 2, and the whole thing's balanced. So this is the balanced chemical equation. Now, when I was a student and an instructor did a problem this easy in lecture, I would totally roll my eyes, and I'd be like, dude, you just picked that one because it's easy, and you didn't want to do a hard one, but I know the stuff on the exam is going to be worse. Now, here's the thing. I actually did this one for a reason. I did this one on purpose because on the exam, you will have problems that are harder, but you will have problems that are this difficulty level. I'll even say that in exams in the past, I have at times put problems, I'll say balance this chemical equation, and it'll already be balanced for you. So there are problems this easy or easier in a whole range of problems that you'll encounter on the exam. So don't roll your eyes or think like, oh, but this is the easiest one, and of course you're going to do this, but I'm not going to get tested on it. You will. I will throw you some softball questions, some easier problems, in addition to some harder ones. But the reason why I bring it up here is if you get a soft problem on the test, don't overthink it. Don't second guess yourself. If it's easy and you got all your things balanced, take the money and run. All right, those problems are gifts, and it kills me when I'm looking over exams that students have taken, and there's a problem like this one, and a student for some reason just can't accept that the problem's easy, and so they like add, like I've seen on tests, like a random 4 added or a 3 or something. Who knows? On a problem that was this simple to balance. So anyways, if a problem's easy, just go ahead and be grateful and move on to the next one. All right, but that's not the last balancing problem we're going to do. I have a few more for us to work through. All right, okay. Okay. Wait, what? Yeah. Sorry, how many more times can I say yeah? Okay. This next problem that I'm going to do is not going to be difficult. I'm going to show you a technique that you can use for balancing chemical equations that will seem like overkill. All right? The technique that I'm about to show you will seem too hard for the example that I'm going to give you. I'm using a simple example to teach you this technique because there are some problems, there are some reactions that are harder to balance that you'll need this technique for. And so as I do this problem, don't write it off like I don't need to learn this because I can just do it in my head. After this simple problem, I'm going to do a more complex problem where you'll need to understand how to use this technique, okay? So with that preamble, let's hit the next example. Let's write a balanced chemical equation for the decomposition of hydrogen peroxide, H2O2. will decompose over time to become liquid water and oxygen gas. I don't know if hydrogen peroxide is a common thing, reagent used. It's a household item. You can buy it at Walmart or Rayleigh's or wherever. And it's used to disinfect wounds. You get a cut when you're a kid, your mom pours hydrogen peroxide on it, it stings and bubbles form. I don't know if you've ever opened a really old bottle of hydrogen peroxide, but when you do, it'll go, you'll hear like this like gas escaping, like a sound. And that's because hydrogen peroxide, H2O2, will decompose into water, liquid water, and oxygen gas over time. So it's decomposing, but the gas isn't escaping because the cap's on tight. When you open it up, that oxygen escapes into the atmosphere, and that's that. It's also another reason if, like, your grandma has a wicked old bottle of hydrogen peroxide, because this thing decomposes over time into literally water and O2 gas, you should probably throw it away because it's probably mostly just water at this point in time. So there's no point in keeping an old bottle of this stuff around. Anyways, let's go ahead and balance the situation. So again, we're going to take our chemical inventory. We have hydrogen and not hydrogen. We have hydrogen and oxygen in this mix. Now, on the reactant side, we have 2 hydrogen atoms and 2 oxygen atoms. On the product side, we have 2 hydrogen atoms and we have 1 plus 2 oxygen atoms. You may be wondering, Josh, isn't that 3? And it is. 1 plus 2 is 3. But I'm keeping them separated for a reason, and it's a good habit to start practicing when you have sources of, when you have the same atom in more than one compound, whether it's on the reactants or product side. It's usually good to separate them out because it'll make the balancing process simpler. All right. Now, you'll notice here that hydrogen is balanced, right? You've got 2 hydrogen and 2 hydrogen on either side of the reaction. So we'd rather not mess with hydrogen if we had a choice. And this is where this problem's a little different. You'll notice we have just oxygen by itself on one side of the reaction, in this case, the product side. Now, here's the deal. We have the opportunity to multiply oxygen, to just change the oxygen count by itself, all right? We can multiply oxygen by some number, which I'm going to call n. And when we do, it doesn't get multiplied by all the oxygen on the product side. It just gets multiplied by the 2 coming from O2. Now, what number do we want to use here? I'm so glad you asked. We have 2 oxygen on the reactant side, and we have 1 plus 2 on the product side. We want to multiply this 2 by some number so that our oxygen balance is right, so that we have the same number of oxygens on both sides of this reaction. What is this number? We got to do a little algebra to figure it out. So we subtract 1 from both sides of this equation. We get 1 on the left side. 1 is equal to 2 times whatever this number is on the right side. Now, if we solve for n, if we divide both sides by 2, we'll see that this number that we want to multiply oxygen by is 1/2. All right, it's 1/2. Now, I need to be very clear up front. You're never allowed to leave a fraction in a balanced chemical equation. All right, you can only use integers in your final answer. But just because we can only use integers in our final answer doesn't mean that we can't use fractions along the way to help us balance, all right? Watch what happens when you multiply O2 by 1/2. We still have 1 oxygen atom coming from water, but now we have 2 times 1/2, which is just 1. Turns out that 2 is equal to 1 plus 1. All right? 2 is equal to 1 plus 1. So right now our equation is balanced. All right? This is a balanced chemical equation. However, as I said earlier, we can't leave a fraction in our balanced chemical equation. It can't be part of our final answer because it doesn't make sense to have 1/2 of an oxygen molecule. That's not a thing that exists in nature. So after including the fraction to help you balance, you have to get rid of it. And the way you get rid of a fraction is you multiply everything in your balanced chemical equation by the denominator. All right? We're going to multiply everything by whatever that denominator of that fraction is. So 2 times H2O2, that'll give us 2 molecules of H2O2. On the reactant side, it'll give us 2 molecules of water, H2O, plus 1/2 times 2 is just 1, so plus 1 molecule of oxygen gas. All right, and this is our balanced chemical equation. All right, this is our balanced chemical equation. Now, you may look at this and go, I could have figured this out without using that whole fraction thing, and you might want to dismiss it. You could. I've no doubt that you could. But you're going to want to know this fraction technique for problems like the next one. All right, so consider the following. Consider the following chemical equation. Let me start by cleaning up my slide. Okay, there we go. All right, so let's balance this situation. This is the combustion of benzene. Benzene is C6H6. We would call that hexacarbon hexahydride. It reacts with O2 gas to produce carbon dioxide gas plus water, vapor. All right, also a gas. We're going to start by taking an inventory. We have carbon, hydrogen, and oxygen on both sides of this equation. On our reactant side, we have 6 carbon, 6 hydrogen, 2 oxygen. On the product side, we have 1 carbon, 2 hydrogen, and then 2 plus 1 oxygen. Again, I'm keeping the oxygen atoms coming from CO2 separate from the oxygen atoms coming from H2O. All right, now let's get to balancing. The simplest one is, to me at least, looks to be carbon. So I'm going to multiply carbon dioxide by 3. When I do, I balance carbon. Wait, what am I doing? I don't want to multiply this by 3. I want to multiply this by 6. When I do, I balance carbon, but you'll notice now I have 2 times 6 oxygen atoms. I need to multiply this 2 by 6. This is another reason why you want to keep them separated. So now I have 6 plus 1 oxygen atoms. And I have 6 carbons. All right, next, we always go with the easiest first, right? 2 doesn't go into 7 evenly, but for hydrogen, 2 does go into 6 evenly. So let's multiply water by 3. When we do, this changes my hydrogen count and my oxygen count as well. Now I have 6 hydrogens and 6 plus 3 oxygen atoms. All right, and now we're in that pickle before that we were in before, where we have to deal with oxygen. Now you'll notice we've got 2 on our reactant side, 9 on our product side, and what we need is to multiply O2 by some number so that 2 times that number is equal to the total number of oxygen on the other side, which is 9. We divide both sides by 2. We see that that number that we need to use is 9 over 2. So when we swing in and actually multiply oxygen by 9 halves, it balances. Right now we have 9 oxygen on the reactant side, 9 on the product side. We've balanced our chemical equation, but we can't leave a fraction in our balanced chemical equation. We can only deal in integers. So to correct this, we need to multiply everything in our balanced chemical equation by our denominator of our fraction, which is 2. So our final answer will be 2 molecules of liquid benzene react with 9 molecules, not of water, holy moly, of oxygen to produce 2 times 6 is 12 molecules of carbon dioxide plus 2 times 3 is 6 molecules of water. All right, and this is our balanced chemical equation. All right, so that is how you balance chemical equations, how you balance chemical reactions. All right, now we're still talking about chemical equations, and we will continue to balance them, but we're going to shift our focus and start talking about types of chemical reactions. All right, types of chemical reactions. All right, so the first type, so the first type of chemical reaction that we're going to touch on is called a combination reaction. All right, and a combination reaction is exactly what it sounds like. A combination reaction is a reaction where you have two or more, doesn't have to be 2, but often it's 2. 2 or more reactants, I'm going to call them X and Y, react, they combine to make one product, all right? So you got X, you got Y, they come together, make a new product, Z. We've actually looked at a combination reaction once today already. An example of a combination reaction would be the reaction of nitrogen gas with hydrogen gas to produce ammonia. All right. It is, in this instance, N2 would be X and H2 would be Y and NH3 would be Z. Now you'll notice something. In a combination reaction, I said it's X and Y come together to make one thing. When I say one thing, I don't mean one molecule, I mean one type of molecule. You'll notice that there are 2 molecules of ammonia made in that reaction, this is still in this reaction, it's still a combination reaction. All right, it is still a combination reaction. So just because I said one thing, I mean one type of molecule, that you're allowed to make more than one type. Or sorry, more than one copy, I guess, of that molecule in the combination reaction. Another example of a combination reaction would be the reaction of nitrogen dioxide gas. Actually, sorry, got the wrong phase. This is aqueous nitrogen dioxide. Can react with aqueous hydrogen peroxide to produce nitric acid. Sorry, there's two of these. Alrighty, so this is another combination reaction. Again, here in this example, X is NO2, Y is hydrogen peroxide, and then Z is nitric acid. All right, so those are two examples of combination reactions. Another type of reaction that you should be aware of is decomposition. Decomposition reactions. In a decomposition reaction, decompositions are, much like combinations, they're exactly what they sound like. It's kind of the opposite, actually, of a combination reaction. In a decomposition, you start with one molecule X, and you produce, it falls apart into multiple pieces, which I'll call Y and Z. You've also seen an example of decomposition reaction today, and that is the decomposition of hydrogen peroxide. All right, aqueous hydrogen peroxide will decompose into liquid water and oxygen gas. And again, X here would be hydrogen peroxide, Y would be water, and Z would be O2 gas. Just like combination reactions, when I say we start with one thing, you can start with more than one molecule of that. So just as with the previous example, where we had things combine into more than one molecule of ammonia, here you can see you're starting with two molecules of hydrogen peroxide, but they're decomposing into water and oxygen. All right. Another example of a decomposition reaction would be nitric acid. Okay, I'm so sorry here. Hang on, I've got to just check in on my screaming child. 1 sec. All right, sorry about that. Hopefully things are under control now. So, where are we? All right, we were talking about a decomposition reaction for aqueous nitric acid. Nitric acid can decompose into, oh wait, hang on. There we go. Okay, I was like, this is a different reaction. Decomposes into NO2, H2O, all right, and O2 gas. You'll notice in this reaction that you've got X, you have Y, you have Z, but then there's a third product. I'll call it, I don't know, A, start back at the beginning of the alphabet. And the reason why I included this is for a decomposition reaction, what makes it a decomposition reaction is not the number of pieces it falls into, but that you start with one thing and it falls apart into a bunch of other things. So anyways, so that's a decomposition reaction. Ariana and Carolina, thank you so much. That means a ton. One of the challenges of quarantine on your guys' end, you feel like, oh wait, I have to be in class, but I'm still, my family's around and things are chaotic. And it's a similar situation when you're teaching normally. It's one of the beautiful things about having a classroom is there's only adults there, so there's no distractions on the learning end, there's no distractions on the teaching end, and you know, here we are, and we're making the best of it, right? Okay. So those are two examples of decomposition reactions. Next, we have displacement reactions, and there's actually two flavors of displacement reactions. There are what are called single displacement, not signal. Single displacement reactions. And then we'll see in just a moment there are double displacement reactions. All right, so but first, starting off with a single displacement reaction. This is a reaction in which you start with some element, X, and then some compound with two, sometimes more elements in it, Y and Z. And the products of this are Y plus XZ. And you can see what happened in this single displacement reaction is Y started out being partnered with Z, and then it swaps places with X, where X ends up partners with Z, and Y ends up kind of free floating. And so you replace or displace one single element. X displaces Y as Z's partner in a single displacement. You heard me now just say replacement. Sometimes these are called replacement reactions. Replacement, displacement, they're all the same thing. An example of a single displacement reaction would be the reaction of solid magnesium metal with hydrochloric acid, which is in the aqueous phase. These two will react to produce H2 gas plus aqueous magnesium chloride. One of the things you'll notice here is on the reactant side, hydrogen starts out being paired with chlorine, and on the product side, magnesium is the one that's paired with chlorine. So you can see that magnesium is our initial starting X, and hydrogen is our Y, because magnesium starts free, ends up getting paired with chlorine on the product side, and hydrogen starts paired with chloride, ends up free floating after the reaction is over. So that is a single displacement reaction. With a double displacement reaction, so it's similar, but instead of one thing changing places, there's two things. All right, so that's single. Let's take a look at double displacement. All right. So with a double displacement reaction, what you have, I'm going to go with, actually, I'm going to call this A and B are paired together, plus X, Y, and the products are A, Y, plus X, B. All right, what happens in a double displacement reaction is the first ion, first cation, will grab the second anion. So you end up with a Y, and then the second cation will grab the first anion, and you end up with XB. So in a single displacement, only one thing is displacing the other. There's only one thing swapping places. Here it's both. It's a double swap type of a deal. So an example of a double displacement would be a reaction between aqueous silver nitrate and let's see, silver nitrate and sodium chloride, also aqueous. And the products of this reaction are silver chloride, which is a solid, and aqueous sodium nitrate. And what you can see right here is silver nitrate, or sorry, the silver in silver nitrate grabs a hold of the chloride to make silver chloride. That would be like your AY situation. And then sodium grabs a hold of nitrate to make sodium nitrate, and that would be your XB situation. So that is a double displacement reaction. All right. Now there's one there's one more, maybe more like two more types of reactions that we're going to talk about kind of in more detail after this, but I want to take a moment to talk about an important distinction for ionic compounds with respect to the aqueous phase and the solid phase. So in a reaction like this one, when you have something in the solid, well, first, let's start with the aqueous phase. You'll notice that AQ is the phase for 3 out of these 4 compounds. And AQ, when you have something in the aqueous phase, this means that that compound is water soluble. All right, it's water soluble. When you have something in the solid phase, in one of these, okay, specifically when something's in the solid phase, in the presence of other aqueous compounds, that means that it is not water soluble. All right, water will not dissolve silver chloride, whereas water will dissolve silver nitrate, sodium chloride, and sodium nitrate. All right, that's the difference. Now, this is clutch. This is super clutch because ionic compounds break apart in the aqueous phase. All right, ionic compounds break apart in the aqueous phase. So whenever you see an ionic compound like silver nitrate, like sodium chloride, like sodium nitrate in the aqueous phase, that means that we might write them together, but they're not actually together. When they're in the aqueous phase, the cation and anion separate from each other. All right, here's what I mean. Here's what I mean. So if you have a compound, for example, aqueous sodium chloride, when you see that aqueous symbol and you recognize that it is a ionic compound, that means that the sodium and the chloride aren't actually together. They're not actually hanging together. If they're aqueous, if they're dissolved, then they've separated into independent cations and anions. All right, they're no longer together. They're a free-floating sodium and a free-floating chloride out in solution. They're not together. If we had, like silver nitrate, like in the previous example. If this is in the aqueous phase, that means silver and nitrate are not associated with each other. So you have free-floating silver cations and free-floating nitrate anions. They're floating in solution. They're not together. Where this gets a little tricky is for compounds like, aluminum bromide, for example. Again, it's an ionic compound in the aqueous phase. That means that they're not associated together. So you have free-floating aqueous aluminum cation together with aqueous bromide anions. Something you should be aware of is in one molecule of aluminum bromide, there are 3 bromide ions. So that means for every 1 aluminum floating in solution, there are 3 free-floating bromides. All right, so you've got to watch your subscripts for your ions because they'll translate into that number of free-floating ions only when the compound is aqueous. All right, this phenomenon of soluble ionic compounds separating when dissolved in water in solution leads us to a special way in which we can write chemical equations known as total ionic equations. All right, the total ionic equation. All right, so let's take a look. Starting with, for example, the single displacement reaction that we saw earlier. So the reaction between silver nitrate, sorry, I said single, double displacement, silver nitrate and sodium chloride producing silver chloride and sodium nitrate. Whoops. All right. Now, when you are asked to write a total ionic equation, whoever's asking you to do this is asking for a very specific thing. All you do is you take every aqueous compound, let me take that back, every aqueous ionic compound in your reaction and separate the anionic and cationic pairs, all right? what the total ionic equation is it says, well, we know that aqueous ionic compounds aren't associated with each other. So let's write them the way they actually exist. All right. And so let's go ahead and do that. Silver nitrate is not associated, it is aqueous. So it actually exists as free floating silver in the aqueous phase plus free floating nitrate in the aqueous phase. Whoops, not the gas phase, the aqueous phase. Sodium chloride, ionic and aqueous, does not exist in an associated pair. They are dissociated in solution. They're a free floating sodium and a free floating chloride ion. All right? This produces, now, here's the thing. Whenever you're in total ionic equation writing mode, it's very easy to just mindlessly split up every ionic compound you see. But when you have something in the solid state, that means that they are not in solution. They're not soluble. They're associated. So if you have a solid compound in your chemical equation, you have to keep those two together. They're not part of the solution. They're a precipitate. They're just hanging out. They're insoluble. They're together. Right? So silver chloride remains associated. Sodium nitrate, on the other hand, is aqueous, so it's water soluble, so it's separated out. All right. So this is then the total ionic equation for this reaction. All right. The total ionic equation is you separate everything out. Now, I want you to notice something about this total ionic equation. You'll notice that on the reactant side, you have 1 mole of sodium cations, and on the product side, you have 1 mole of sodium cations. I also want you to notice on the reactant side, you have 1 mole of chloride anions. Nope. We don't have a mole of chloride anions on the product side, but we do have 1 mole of sodium or of nitrate anions on the product side, and we have 1 mole of nitrate anions on the reactant side. Whenever you see something on the reactants and the product side of a chemical equation unchanged, that means that those species, whatever they are, ions, atoms, whatever, didn't actually participate in your chemical reaction. If they're on both sides of the equation and they're unchanged, they didn't participate. You'll notice that silver is on the reactant side as silver cations. It's on the product side, but as solid silver chloride. It changed. Same with chloride. It's an aqueous anion on the reactant side, but now it's associated. It's part of a compound silver chloride that's a solid on the product side. It changed. But sodium is an aqueous cation on the reactant side. It's an aqueous cation on the product side. Unchanged. Same with nitrate. These ions have very special names, a very special name. They are called spectator ions. All right, sodium in this reaction and nitrate are 2 examples of spectator ions. They do not participate in the chemical equation. All right, they're just watching. They're just watching it happen. They're the spectator ions. And we do something very special with spectator ions. We cancel them. All right, when you cancel your spectator ions, you get something known as, you cancel to get the net ionic equation. All right. Now the net ionic equation says, the total ionic equation says we want to write all of these ions as they actually exist in solution. So if they're not associated together, we're going to write them as they are in solution, free floating, not associated. The net ionic equation says I don't care about spectator ions. I only want to see the species, ions and molecules that are actually changing, that are actually reacting, that are actually participating in the solution. Sorry, in the reaction. So to get your net ionic equation, you take every spectator ion and you cancel it out. All right? You cancel out your nitrates, you cancel out your sodium, and what you're left with is just the only ions and molecules that actually participate, that actually change in the reaction. All right, so in this case, we get an aqueous silver cation reacting with one aqueous chloride anion to produce one molecule of solid silver chloride. All right, that is the net ionic equation. All right. That is the net ionic equation. So the net ionic equation and the total ionic equation are connected, all right? You actually write out the total ionic equation as a step to get to the net ionic equation. The total ionic equation, you break up every aqueous compound, aqueous ionic compound in your reaction. Then you identify your spectator ions, cancel them out, and write your lean net ionic equation. The way to think about this is this is like different ways of looking at the same thing. So like if you're watching a basketball game, you've got that wide angle shot where they pull back and you see the whole stadium, you see all the audience and the action that's going on in the court, right? That's like the total ionic equation. The net ionic equation is when the shot hammers in on just the court. You don't see who's in the crowd. You don't see Jack Nicholson sitting there with his glasses, right, at every Laker game. I'm from Southern California, so I grew up watching the Lakers. I apologize. Oh, wait, no. Sorry. I was about to say, I apologize to all you Kings fans out there. Southwestern is not in Sacramento. I'm streaming to SoCal. So what are you guys? Well, Clippers are LA too. Anyways, maybe you're Lakers fans too. I'm just used to apologizing for rooting for Southern California teams. Anyways, so maybe the Jack Nicholson reference is fine. He's part of the total ionic equation where you see everything, players and who's watching the game. Net ionic equation, you're just watching the action on the court. That's the point. Now let's go ahead and use this information to do another example of this, where we write the total ionic equation followed by the net ionic equation. I'm just going to title this part Ionic Equations. All right. All right, let's do an example. All right, let's do aqueous zinc chloride reacting with sodium carbonate. Whoa, sorry. I said sodium, but then I wrote nitrogen. Sodium carbonate to produce sodium chloride and zinc carbonate. All right. First step, we write the total ionic equation. We are going to identify every aqueous ionic compound in this reaction and separate them out into cation and anion, not pairs, individual cations and anions, because that's what it means to be dissolved in water if you're an ionic compound. So zinc chloride is one free-floating zinc cation together, not together with, but floating alongside two chloride anions. You got to remember, when you have more than one anion or cation in your molecule, when you write them separated, you have to include the number of anions present. So we have two chlorides and zinc chloride. When we write them as free-floating pairs, we have to write two chloride anions. You'll see the same thing in this next compound. We have sodium cations, so aqueous sodium cations, and we have carbonate anions. There's another polyatomic. Now, because we have two sodium cations in a molecule of sodium carbonate, we have to write 2 out in front of our sodium because there's 2 of those cations floating in the solution. Now the product or products are going to be, now we have sodium chloride. Now, even though there's only one sodium cation and one chloride anion floating in solution, because we have 2 of these molecules, we need to have 2 sodiums and 2 chlorides in play. Finally, you'll notice that zinc carbonate is in the solid phase. We are not, therefore, going to separate them because they remain associated. They're not water soluble, so they're together. They're one solid compound. That looks a little like a G. Okay, so this is the total ionic equation. All right, this is the total. Right here. Next, let's write the net ionic. All right, the net ionic equation. Now we're going to get to the net ionic equation by identifying our spectator ions and canceling them. The first spectator ion I see is chloride, right? We've got 2 on each side, so those will cancel. The next spectator ion I see is sodium. You'll notice that we have 2 on the reactant side and 2 on the product side. They cancel as well. Everything that's left, everything that doesn't cancel, is part of our net ionic equation. And even though we do have zinc on the product side and reactant side, we have carbonate on the reactant side and product side, they don't cancel because they've changed. They went from being dissolved in solution to being a solid compound together. So because they've changed, they don't cancel out. And our net ionic equation will be aqueous zinc anions reacting with aqueous carbonate anions to produce solid zinc carbonate. All right. And that is our net ionic equation. All right, that's how you handle it. Whenever you're asked to write the total ionic equation, split up all your aqueous stuff. Whenever you're asked to write the net ionic equation, you still have to write the total ionic equation because you still need to split everything up to identify your spectator ions. Once you've identified your spectator ions, cancel them out, Whatever's left over is your net ionic equation. Cool? All right. There's one last type of reaction we have to cover here. Well, two. One last type of reaction that we have to cover in brief, and then we'll dig into the other one. So the first one is combustion. All right, combustion reactions. Combustion reactions are actually. All right, so a combustion reaction is a reaction where you take any element and you react it with oxygen gas to make what we call an oxide. So this right here, X is any element reacting with O2 to make an oxide of some kind. So for example, you could have a magnesium metal, solid magnesium, reacting with oxygen gas to make MgO, magnesium oxide. All right, this right here, magnesium oxide. And this is coming from magnesium metal. All right. You could have, for example, hydrogen gas, the combustion of hydrogen. Hydrogen reacting with oxygen to produce dihydrogen monoxide, aka water, right? But water is just a hydrogen oxide. It's the oxide of hydrogen. The most common type of combustion reaction you're going to come across is the combustion of hydrocarbons. So for example, any of you who used a gas stove this morning did this reaction. You were doing a chemical reaction, chemical experiment, even if you didn't notice or know it. Our stoves burn CH4. And so it is the combustion reaction between CH4 and O2 to produce. Now this is interesting. I should really say this is an element or compound. Doesn't have to be an element, as you can see in this example. But you'll notice that there are two elements here. There's carbon and hydrogen, and the two products are a oxide of carbon and an oxide of hydrogen, CO2 and water. So whenever a hydrocarbon is burned, gas stoves, propane grills, our cars burn octane. Whenever a hydrocarbon is burned, you get two oxide products, carbon dioxide and dihydrogen monoxide, or water. All right, so combustion reactions are adding O2 to make an oxide or more than one oxide, as we do in this case. All right. Now, there's, I think, one last reaction type we got to cover in this chapter, but it's a long one, so this one's going to take us a while. We'll start the discussion today. We'll pick it up on Thursday. We need to talk about redox reactions. redox reactions. Now, redox stands for reduction oxidation. All right, so this stands for the read in redox stands for reduction. And the ox in redox stands for oxidation. Oops. All right, so reduction oxidation reactions. If we're, going to study redox reactions, it might be a good idea to know what reduction and oxidation are. Right, so oxidation your book has several definitions for it. They're like, oxidation is making bonds to oxygen, or breaking bonds to hydrogen, or making bonds to, like, all sorts of things. They throw around all sorts of things. But the nugget of it, the thing that's true, this is the one that you got to remember. Oxidation is losing electrons. Losing electrons is oxidation. Reduction is the opposite process. Reduction happens when you gain electrons. All right? That is what reduction is every time. It's gaining electrons. What oxidation is every time is losing electrons. There's a bunch of acronyms that you can use to remember what oxidation and reduction is. This one's my personal favorite. This is the lion I draw for my 2-year-old. When he's having a bath time and there's like fog on the glass, he'll ask me, "Daddy, draw a lion," and this is how he looks. So you should feel bad for him because he thinks this is what a lion is. But this lion's name is Leo. And you'll never guess what he says. Well, like any lion would say, Leo says, "Grr." All right? Leo says, "Grr." Leo is an acronym that is lose electrons oxidation. Lose electrons equals oxidation. GER is an acronym that means gain electrons is equal to reduction. And if you can remember my crappy drawing, you know oxidation and reduction now. Leo says GER. Gain electrons. Reduction is the GER part. Lose electrons. Oxidation is the Leo part. All right? Now, oxidation reactions occur when both of these things happen simultaneously. All right? That's the way to think about oxidation reactions. You can't have reduction happen without oxidation happening. All right? If something's losing electrons, that means something else is gaining electrons. If someone is buying, that means someone is selling. You can't have one without the other. So would you like to see an oxidation reaction? I'm going to assume that your answer is yes, even if you don't. It's on the exam, so you'll probably want to see it at some point. Here's an oxidation reaction, for example, one in which electrons are exchanged. Oxidation and reduction happens. Something loses electrons, something gains electrons. Here's your first example. You may be noticing a theme of me doing ominous foreshadowings today, showing you a reaction, then bringing it back around and being like, oh, that's a combination reaction, BT dubs. That's whatever. Here's an oxidation reaction you've seen today. The combination reaction of H2NO2 to make H2O. You'll also notice, funny story, this is a combination reaction. Two things combining into one. It's a combustion reaction, hydrogen reacting with O2 to make an oxide, and hat trick, it is a oxidation reaction. Now you might say, wait a minute, Josh. You told me that in a redox reaction, something's oxidized, which means it's losing electrons. Something else is reduced, which means it's gaining electrons. So if this is a redox reaction, electrons are being exchanged. Someone's losing, someone's gaining, but I don't see any electrons. I don't see any charges. I don't see something getting positive. I don't see anything getting negative. Where are the electrons? I thought this was a redox reaction. And it is. Here's the thing. Redox reactions are like drug deals. Somebody is buying, and someone is most definitely selling. But to you, the outside observer, it looks like everybody is just enjoying pollos hermanos, right? It looks like everybody's just eating fried chicken. That's how drug deals go down, in a public place, and it's between two people doing normal things, all right? Your job for the redox section of this course, your job is you're the DEA agent. You're here to bust the seller and the buyer. You need to identify who's bringing the electrons. You need to identify who's taking the electrons. And that is what redox reactions are all about. And that is the cliffhanger I'm going to end this lecture on. So coming back Thursday, we're going to pick up with redox reactions and we'll learn how to determine, who's selling electrons, who's buying electrons, who is reduced, who is oxidized, all that business. We're going to make a bust next lecture on these redox reactions. So stay tuned if you can. If you can't live with the suspense, you can always, you can't watch the next episode, but you can read ahead in the book. You can read the book, right? And then you can be one of those people where you're telling everyone else like, oh, I know what happens next. I read the book before I watched the show. There's nothing wrong with being one of those people. All right. That does it for lecture tonight. I will see half of you in lab at 6:45 in about 15-ish minutes.